but you learn those skills just to have the ability. You don't always need to use those skills after a certain point. Does that make sense? So in math, in algebra, this is where you would stop. You would actually not do that because it's more usable this way for the things we want, generally speaking. But notice before I left my answer like that, I did a prime factorization exercise which showed me what to do. This topic, so when you guys look up above, you'll see all these topics listed in math. We have fractions, decimals, percents, graph. So that part is a lot of pre-algebra. Then you get into graph inequalities, systems of equations, polynomials, and so on. These are algebra topics starting from here, even though solving equations is one we're going to do right now. But when you get to this topic right here above me, these two topics, polynomials and factoring, they actually use the same skill set that you would use in all these problems I just did. So I was just doing pre-algebra, but notice that when you get to these chapters here, your brain is literally going to say, I remember doing that, but I did it with numbers. Now I'm going to do it with letters. Let me show you an example. If somebody asks you, what is a cubed times b cubed divided by a squared? That is the same thing as literally saying a times a times a times b times b times b divided by a times a. And I cancel the a's. The same way I canceled numbers back here. So the same skill is mirrored over here with letters that is used there with numbers. Do you see why nobody should do algebra if they're bad at pre-algebra? Like, don't even do it. Just go play outside. Don't touch it. If you don't know, if someone doesn't know how to add, subtract, multiply, divide fractions comfortably, they shouldn't do algebra. But if they know how to do those things, then they should do algebra. Now, if you're trying your best and you still don't know how to add, subtract, multiply, and divide fractions, you need to find multiple different textbooks. It's really unfortunate that sometimes we teach people as though the only textbook they have is the only option they have. But this is not 1225 AD, right? We're not living in the days of the start of Oxford and Cambridge. We're living in the new era where you can have 1 million textbooks that talk about the same concept. So why not look at a different textbook rather than the one you have in front of you? Does that make sense? So we need to know how to do this stuff. And now, of course, we've talked about how it applies to algebra. In algebra, we give you letters and we ask you to simplify based on these details, like what's right before you. This is called an exponent. A to the third, that means that A occurs 3 times, right? It's the cube. A times A times A. That's A cubed. What is B cubed? B times B times B. What is A squared? A times A. And we simplified it. That's called polynomial simplification we just did. That's from chapter 5 of an algebra textbook. Like, this is from the middle of an algebra course. And you're looking at it and going, that's easy. Yeah, algebra is actually not bad at all. Without algebra, however, you can't do calculus. So you notice the pattern? You need to do pre-algebra well so you can do algebra. You need to do algebra well so you can do calculus. Why do you want to do calculus? Because it's beautiful, period. Not for any other reason, but because it's beautiful. Okay, now let's go back. We're going to do equations. I'm going to take you through 1-step equations, 2-step equations, 3-step, well, not 3-step. 1-step equations, 2-step equations, multi-step equations, and then equations with formulas, and then we'll take a break, okay? Does that sound like a plan? You're good. And you don't have to worry. You can talk out. It won't catch you as much. It's catching me just to that. Okay, so I'm going to clean all these, and then let's do some problems from algebra. So now that we've gotten ourselves established, give me 1 second. Okay, so algebra. Algebra as a field of study came around 600 AD. That's when it came. So let's clean this off. Okay, man. Can someone invent a board cleaner? Because this is a lot of cleaner. Would you guys agree? I'm hoping this helps me with my pickleball game later if I have to do this. Okay, so. Okay. Okay, let's do something here quickly. So again, when you think about mathematics, there's a pattern of topics people learn. Of course, you do elementary school arithmetic, we call it addition, subtraction, multiplication, division. Then when we get into pre-algebra, which pre-algebra, again, applies to everything, addition, subtraction, multiplication, division, and fractions, decimals, percent. That's all pre-algebra. Pre-algebra is pretty much anything before algebra, which means that kindergartners are doing pre-algebra. And I'm not saying that to sound all smart, but that's the reality. They are in pre-algebra. They are before algebra, right? So that's pre-algebra. This is where pre-algebra is almost like your free throw ability. It's your ability to work with numbers. Your number sense needs to be strong. If you give me a number and you tell me to multiply by another number, I should be able to estimate, round, deal with the numbers in my head as best as I can. Unfortunately, many Americans cannot do that. And that's why you go to certain stores to buy certain things and people are giving you the wrong change, even though they have a computer, but it's because their number sense is off. So you need to make sure your number sense is working, and that's why I do not think summers off from pre-algebra is a good idea, because it's like your free throws. You need to do it a lot, right? So you have to stay consistent with doing it. So that's what pre-algebra is. Today, we've done a little bit of pre-algebra. We talked about prime numbers or prime factorization. So that was one of the things we talked about, was prime factorization, which is probably, in my view, one of the most important topics in all of pre-algebra is prime numbers and prime factorization, because if you know how to prime factorize, then you know how to break numbers down. And if you know how to break numbers down, then you know how to find the lowest common denominator. That means you can add and subtract fractions, and you're good to go. But where did we get prime numbers and prime factorizations from? Well, part of that came from Euclid's book, The Elements. So Euclid was Greek. So we get prime numbers from his book, which we have available to you guys on the back table there. But Euclid's book basically has a section where he introduces us, and this idea of prime numbers is discussed. So we have Euclid's work, or his work introduces us to prime numbers. He was Greek, okay? And Euclid, now we're talking about, I would estimate about 300 BC, okay? So let me just estimate the work around 300 BC. We could check it with the exact date later. But again, let's think of the days of Pythagoras, Socrates, Plato, Aristotle. All of that would be, again, around that 570 BC. I believe Pythagoras was born around 570 BC, and then it brings us into Euclid's work, which is later on around, again, 300 BC. So we have Pythagoras, we have Euclid, Socrates, Plato, Aristotle, Archimedes. Those are the big names in the Greek history, right? So when we're talking about the history of math, elementary school math, as far as addition, subtraction, and some of that would go back to, of course, the days of Abraham, Isaac, and Jacob. This is way back. How many cattle? How many goats? That was what math was heavily involved with. It's just counting calendars, understanding seasons. Back then in Egypt, right? Egypt was one of the centers of civilization, one of the greatest civilizations and empires back then. They actually gave us fractions. So notice that math and history kind of, bringing it together, I think is very interesting. So prime numbers came from the Greeks. Before the Greeks, we had some work from the Egyptians and the Babylonians and the Persians. And so when you think about 60 seconds and 60 minutes, that came from the Babylonians. That's from the base 60. We're using work from the Babylonians today. That's what we do when you talk about what's the time. You're using the Babylonian system. The Egyptians gave us fractions, and Egyptian civilization was probably high up there around 1800 to 1500 BC. So they gave us some work there. They built those pyramids, which I don't believe in aliens, but you just look at those and see, and it's amazing, the pyramids that they gave us, right? So the Egyptians knew something about math that we need to learn. The Babylonians came, the Persians came. Now the Greeks have given us prime numbers. Prime numbers are now tied back to fractions. And then the next level, after you've mastered these, of course, and the fractions, as I said today, was I was going to introduce you then to equations. Equations come from more of, I'm going to write it right here. It actually came, well, not equations by themselves, but algebra. Part of the history of algebra goes back to Iraq around 600 AD. And so around 600 AD, a librarian by the name of, I don't know how to pronounce his name well, but you can look him up. He was a librarian in Baghdad, and he gave us some of these concepts we teach in algebra, including equations. And so when you look at the history of math, we've gone from 2000 BC to about 500 BC, where we have the Babylonians and the Egyptians and the Israelites. And then from 500 BC to about 500 AD. Right, a lot of things happen there. The Romans come. We talk about Roman numerals. So you see the influence of different civilizations on math. So around 500 AD, 500, after Jesus comes and he dies and he leaves, the Roman Empire rises. We have the Roman Empire and the regime all the way till about 400, 500 AD, and then the Islamic Empire is happening, and that's part of where this guy in Iraq gave us part of the things we talk about in algebra. In algebra, here are the topics that are covered: equations, graphing, inequalities, systems of equations, polynomials. So I'm just going to write all the topics we cover in algebra, and then we'll zoom in on some of them. Factoring. Okay, so in a typical Algebra 1 course, this is what's covered in the whole course. Like I'm giving you the whole lecture of the whole course. This is the whole Algebra 1 course. It's equations, graphing, inequalities, systems of equations, polynomials, and factoring. So when you go to school in the fall, there's no topic that is mentioned that your brain is going to say, I don't know that. No, you're going to know it all. Well, you still be humble and respectful. But what I mean is you're going to know the whole picture. So you have the whole picture right here. So the very first major topic is equations in algebra. Graphing, some of the graphing we do came from a French mathematician named René Descartes. That's more like 1500 AD. So this is way after algebra. 1,000 years after algebra was born is where we started doing some of the work we do in graphing. Inequalities and equations are very connected, so I'm just going to leave those alone. Systems of equations, some of that work was done in the 16 and 1700s by Swiss mathematicians and German mathematicians. Polynomials and factoring, that's another history. We'll just have to look at it another time. But basically, we've done a little overview of math history from Abraham, Isaac, and Jacob, where they were just counting, all the way to things like prime numbers, all the way to things like equations now where we are. So an equation simply is a relationship between two expressions that in order for it to be true, in this case, for example, x would have to be 5 in order for that expression to be true, right? So then the left side is 10, the right side is 10. That's called a one-step equation because it takes one step to solve it. Now, what I use to solve this equation now is called intuition. Some people do that. Some people who are very good in math use intuition a lot, and they don't take notes. They're very fast, and they look at the problem, they have the answer. I'm not against intuition, but not every problem is going to be basic like this, right? This is called a one-step equation. You can use intuition, or you can use a systematic approach to solve it. So now let's use a systematic approach to solve it. So if someone says x plus 5 is equal to 10, we subtract 5 from both sides. Why are we doing that? Because whatever we do to the right side, we have to do to the left side. So then x is equal to 5. We have done it systematically so that no matter what type of problem we're faced with, so someone says, what is x plus 17 is equal to 128? I don't have to sit there just trying to do it with intuition. I can also just write minus 17, and that gives me 111. Right? So basically, I'm using a systematic approach to solve the problem. So mathematics gives us systematic tools that you can apply in a situation, and if it works in that situation, it probably will work in another situation. Let me give you an example, and then we'll take a few more practice problems from equations. So imagine you have a farm and I have a farm, which is what most people did in Western civilization back around 2000 BC. That was the main stuff, right? It's not like people going to their neighbors' houses asking, hey, what did you watch last night? No, the only thing they were watching was cows, okay? So how many cows do you have? And so life was very simple, right? Egypt, of course, gave us, we talk about the Fertile Crescent, and a lot of stuff happened out of that area of Israel, Egypt, and that area, right? So right there, if I had 100 cows, and someone else had 100 cows, and you and I came and we're like, how many cows do we have total so we know how much land we need? One way to do it is to manually count. Okay, let's count Mr. Tarfa's cows. 1, 2, 3, 4, all the way to 100. And then we would count your 100 cows. 1, 2, 3, 4. Okay, so you have 100, they have 100. Now we say, how do we add those together? One way to do that is to count all my cows, then go over to your farm and just count from 101, 102, 103. And when I do that, I find out that there's 200 cows, and we're happy. Make sense? But here's another way to do it. What if one cow represents the number 1? Okay? And 2 cows represent the number 2. And what if we use that representation, and instead of counting to 100 cows, what if we just said, since one-to-one relationship exists, that means 100 cows has to equal some number 100. Now, granted, the number 0 wasn't here then, okay? That's another story. Where do we put it? There's actually a whole book. Like there's these books on math history. This one is on pi. This one is on Fermat's last theorem. This one is on Fibonacci. We talk about the Fibonacci sequence. There's a whole book like this, which I have in the back, in one of my boxes here, which is called Zero, the history of zero. So at this point, we don't really have zero as an operation that we use as much, but let's just use it for a second, okay? This is back 2000 BC we're talking, okay? So 2000 BC, let 100 cows represent the number 100. Then we go to your farm, and we know that you have 100 cows as well, and let the number 100 represent the number of cows you have. When we add these numbers together, we get 200. Then we translate it back and say that means there are 200 cows. So, again, look at the situation. Instead of counting the cows individually, why don't we represent 100 cows equals the number 100? Then let's take that number 100, use it to manipulate, do arithmetic manipulation. Whatever manipulation we do with those numbers, we can bring it back to reality and say that's how many cows that person has. This to us is simple, no problem. That's not the case when you live 2000 BC. Like, we take a lot of things for granted because we live today. But do you know that if you lived 100 years ago, you wouldn't be able to get to California in a day? If you lived 100 years ago, it would take you a long time to go from Fargo to California. And then if you wanted to go to England, you wouldn't be getting there tonight. That's not possible, right? So if we think about the technological difficulties they would have faced, it will probably make us be more appreciative of the things that we have. And so back then, a lot of counting had to happen. But what math does is that instead of counting it, you change it to numbers, you work with the numbers, and the answer you get with the numbers is the answer you would get if you were to count the cows individually. So algebra is kind of a similar thing again. You work with these equations, and the answers you get to these equations are solving some big problems. So this is one-step equation. You just either use the opposite operation. So when you solve one-step equations, you need to use the opposite operation in order to get the answer that you need. So let's talk about that for a second. So we're going to talk about opposite operations. Okay. So x plus 5, we subtracted 5 from both sides, and we got 5. Why did we subtract 5 from both sides? Because in the original problem, there was an addition. And what you do is you use the opposite operation to get the answer. So what is the opposite of operation of addition? Subtraction. So that's why we did that. And if you don't mind, I'm just going to use the symbols for the remaining. So then if someone says, what is 2x is equal to 10, the original operation is multiplication. So then what do I need to do to solve the problem? I use division. So 2x is equal to 10 will become x is equal to 5. Okay, so I'm using the opposite operation to get the answer to the question. What if it was x divided by 2 is equal to 10? The original operation is division. So then what I do is I have to use multiplication, the opposite operation. And so it becomes x over 2 is equal to 10. You multiply both sides by 2. You get x is equal to 20. And then the next one, if you have x minus 6 is equal to 12, the original operation is subtraction. So then I have to use addition, which will give me x minus 6 is equal to 12. You add 6 to both sides. X is equal to 18. So how do we solve equations? Use the opposite operation of the original thing in question, and that will give you the answer to any one-step equation. So in all these problems here, we had a certain original operation, and we used the opposite operation to get the answer that we need. This is how we solve one-step equations. How about if we step it up? How about two-step equations? So in the book that we use for algebra, called Tyler Wallace Algebra, again, I've had many books in my life, but the one by Tyler Wallace I love. It's one of the best algebra books out there. Why do we like it? Number one, it gives you examples, a lot of examples. Every math book should have a lot of examples. Why do we need examples? Because we need people to see the patterns. Now, people see patterns at different rates. The best mathematicians are the people who can see patterns the fastest, right? If I can see a pattern, and what do I mean by a pattern? Again, if I go into a neighborhood and the address is showing up like this, and then I get to the next house on the block, I know it's going to be 109. That's a pattern. Now, that's a pretty easy pattern. But there are some other patterns that, again, people have seen. Great minds. This guy, Fibonacci, was very good at math. And of course, he gave us things called like the Fibonacci sequence. And we'll do that before we end. We'll talk about Fibonacci at the end here. But basically, if you want to be good at math, improve your pattern recognition skills. And you know the funny thing about pattern recognition skills is that they're actually very good in sports also, right? One of the best basketball players today is a man by the name of Nikola Jokic, right? Jokic is a center for the Denver Nuggets. He's not a point guard, but he sees patterns well. And some days, if I'm having an intense day and I just need to cool down for a second, I just need to watch some Jokic assist videos. Because the assists that he gives in basketball are unbelievable, right? I play as a point guard in basketball when I can. And so one of the best things that a point guard could do is to be able to see patterns. Kellen is going to cut to the basket there. I'm just going to drop the ball for Kellen because I know he's going. I know the pattern. We have a system. So math teaches us about patterns. Now, Jokic is a center. And centers generally are trying to just get the ball, put it back in the basket or whatever, mostly in the paint, working close to the net. But Jokic is dangerous because he also passes like a point guard. So his basketball IQ is very high. But honestly, part of it is his pattern recognition is very good. He's very good at recognizing certain patterns on the basketball court. So the idea of pattern recognition is one of the ingredients. So pattern recognition is one of the ingredients that can help anybody be excellent at math and science. So how do you improve your pattern recognition? It's not just by doing math, even though that's important and you should do math. But honestly, there's books that have been written, like Sudoku puzzles. Like, there's things that you can do that just help your pattern recognition. Once your pattern recognition improves, your math is going to be excellent. If your math is excellent, your life will be 1,000% easier in living in today's world. If your math is good, life will be pretty easy. So that's number one. That's number one reason we love Tyler Wallace. He gives you a lot of examples so you can see the patterns. Number two, the Tyler Wallace book we use for algebra has a lot of practice. Some of you might have seen it. A lot of practice problems that are very specific to the topic in question, like 20 practice problems. And then number three, it does have a solutions manual that comes with all the odd problems. So the reason why we like our algebra book is because it gives you a lot of examples and gives you patterns, it gives you practice problems, and then it gives you a solutions manual. With that said, in the algebra book, 1.1 is one-step equations. 1.2 is two-step equations. What happens if you have a problem like that? What if I change it and say 2x plus 6 is equal to 12? Well, now I can't just get the answer like that. Granted, people with intuition know what the answer is. But what do we do next? We have to subtract 6 from both sides, and then we get 2x is equal to 6. Then we divide both sides by 2, and x is equal to 3. So let's take a step back on how we did this problem. In order to know how we did this problem, and by the way, some textbooks will go beyond these topics, but if you master these topics, your Algebra 1 is pretty solid. And Algebra 2 sometimes actually starts with polynomials again and repeats it. That's why I teach Algebra 1 and 2 combined. I think Algebra 1 and 2 should just be done together. Like, I'm on your side. I want you guys to finish your math efficiently, quickly, and that's why I do Algebra 1, Algebra 2 together. Therefore, you could do it both. You could do both of them in a year if you want, and then you could take the CLEP test, which I was actually teaching today. I have all these books for you guys. It basically gives you college credit for math. Okay, so how do we solve a two-step equation? In math, you guys have learned of something called PEMDAS. And PEMDAS is parentheses, exponents, multiplication, division, addition, and subtraction. But did you know that if you go in the opposite direction, it forms something called SADMEP? So in pre-algebra, you use PEMDAS. In algebra, you use SADMEP. And you use SADMEP because let's examine this and then we'll land the plane with Fibonacci, okay? So what is SADMEP? SADMEP is saying we should do subtraction and addition, division or multiplication, and then exponents and parentheses in that order when we're solving equations. Now remember with PEMDAS that these two are of equal rank, but you do them from left to right, whichever one occurs first. Remember with addition and subtraction, you do it from left to right. But these two are above in rank. That's how PEMDAS works. So let's talk about SADMEP as it relates to solving this problem here. So it was 2x plus 6 is equal to 12. There's an addition of 6 here. So according to SADMEP, I do any addition problem piece first before I do the division or multiplication piece second, because between 2 and x there's a multiplication there. So I subtract 6 from both sides, then I divide both sides by 2. Notice I did addition subtraction first before I did multiplication division second, but in PEMDAS you put multiplication division first and then you do addition subtraction. Well, this is in simplifying expressions. So when you're simplifying expressions, that's what you do. However, when you're solving equations, then you use SADMEP. Okay? So if you use SADMEP, your equation solving skills will be excellent. Let's land the plane with Mr. Fibonacci, and we'll call it a day. So we've talked about why we love Tyler Wallace. Everybody here, I'll get you guys the book. Some of you do have the book already. Let's clean this part up. And okay, so we've talked about one-step equations and two-step equations. There's something called multi-step equations. When we get back together, so between now and next Monday, I want you guys to do the odd problems from one-step equations or two-step equations and multi-step equations. But for multi-step equations, you might want to spend more time watching the videos if you have questions, or talk to anyone you want about it as well. So 1.1 is one-step equations. That's where we just have one step. We've discussed that. 1.2 is two-step equations. And 1.3 is multi-step equations. Okay, so before we discuss Fibonacci, which will only take me a second, this is, if this blows your mind, it's okay. I just want to stretch your mind for a second. This is a multi-step equation. In order to do a multi-step equation, you have to distribute the number on the outside inside. So this becomes 2x plus 10 is equal to 15. All I did was I distributed the 2. It's called the distributive property. And now I add like terms. So this becomes 20. So 2x plus 20 is equal to 15. I subtract 20 from both sides. And I get 2x is equal to negative 5. Please note that this is not the lecture on 1.3 in detail. I just want to gauge where people are at. And if you feel stretched, that tells me that you need to stop there. But if you feel this is still too easy, then I need you to keep going. Math needs to be done on the basis of how comfortable people are. And if you're comfortable with the topic, keep going. Don't stop. Keep running, right? Just keep running until you get to calculus, the promised land of mathematics. Okay? So 2x is equal to negative 5. You divide both sides by 2. And x is equal to negative 5 over 2. If you were in an algebra course, you do not want to write that as a mixed fraction. Do you see what I was getting at in the beginning? We don't want you to change that. You're done. Like, life is too short to be changing improper fractions to mixed numbers in algebra. You're done. So let's end with our friend, Fibonacci. Fibonacci was a mathematician who did some amazing work, one of which we talk about called the Fibonacci sequence. This book is called Fibonacci, A Man of Numbers, Fibonacci's Arithmetic Revolution. And the author here is going to go into detail discussing our friend Fibonacci. One of the things that he's talked about, this is about 1200 AD. And by the way, the oldest university in the world is in what country? In the Western Hemisphere. Where is the oldest university in the world found? Italy. Okay, so it's in Italy, called the University of Bologna. And so Fibonacci does some work, and he gives us one of the things called Fibonacci sequence, which we're going to end with. And here's how it goes. If I take the number 1, okay, and I add 1 to it, then it gives me the number 2. If I take the number 1 plus 2 and I add those two together, I get the number 3. If I take the number 2 plus 3 and add them together, I get the number 5. If I take the number 5 plus 3 and add them together, let's see, where do I want to put this? I'm going to put this here. It gives me the number 8. If I take the number 5 plus 8 and add them together, I get the number 13. You guys get the gist of what I'm doing? So I took the number 1 and then 1. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8. 8 plus 5 is 13. 13 plus 8 is 21, and so on and so forth. Do you see what's happening there? That's called Fibonacci sequence, and it describes certain phenomena in life. Did you know that the Fibonacci sequence, which is a mathematical expression, is what calculates or shows the back of a snail? Mathematics is found in nature. Back of a snail, sunflower seeds. There's mathematical equations and expressions in living organisms. That's weird. I don't think you guys, that's weird. You could do this math and then find it like even another one is exponential functions. Now, this is not necessarily Fibonacci, but even how bacteria grows, it follows mathematical formulas. It's bizarre. Like the math is over here. Nature and organisms are over here. But then we find out that, wait a second, there's symmetry in nature. So if life is an accident and there's no creator and so on, which some people believe, guess what? How do you explain the back of a snail matching math equations? How do you explain sunflower seeds? How do you explain, and we could go on and on. There's a ton of them. How do you explain bacterial growth matching with mathematics? Again, these were two separate entities, but we're seeing them come together. So Fibonacci gave us some of this description, which I think was supposed to describe rabbits. I don't know if you guys know rabbits can have a lot of children over time, and there's also a use of that with that. So anyways, that's some of what we talk about with Fibonacci. I will discuss a little more about it next Monday, but between now and next week, why don't we try doing one-step equations, two-step equations, and multi-step equations? Does that sound good? It's a lot to chew on, and I'm sorry, but I'll stop there. I'll send you guys the homework reminder, but you guys are dismissed. Or if you have any questions, let's take them now. Questions, thoughts, comments, objections. Okay, where do we go from here? Odd problems from the Tyler Wallace book from 1.1, 1.2, 1.3. And I'll talk more with you guys about it too, because I've shown it to Caitlin. I don't think I've shown it to Kellen, and I'll show it to you guys. Sound like a plan? Okay, let's go to computer science, those of you who are staying. And then Caitlin, we are all done.